Let's talk about the seat ring. That's this part of the check assembly. Remember, the check opens and closes, and the rubber part of the clapper comes and sits against this. And it turns out that this is a very critical part of the design. If it's too sharp, it cuts the rubber. If it's too wide, it doesn't seal well enough at low differential pressures with the spring. And so this was very, very critical that we get this part right. So that's an important part of the design and how it relates to the height of the rubber, the EPDM on the clapper. So that's part of it, and it's got a special thread. You'll note when we get to that part, there's a special thread, and then there's these pockets that hold the spring and hold the clapper itself. And there's parts that you don't see. There's spacers and rods and shims and springs and cam bars and rollers and things like that. But for the seat ring itself, what you're going to need to know is that the seat right here, that's an important area. The thread is important. Oh, and there's an O-ring, right? And so the O-ring has to sit. Let's see if I can get that to show a little bit better. The O-ring has to sit on this surface, and that's a modified O-ring groove. Just because of the nature of this, it's modified just a little bit to fit slightly different, and that was due to the machining of the mating part and how that worked. Okay, and so again, we're going to make this from a blank. This is going to be an injection molded blank that then we're going to put on a machine tool and put all these fancy parts in it. And that's because all the tolerances are too close. It's too precise. It's too tough of a part to make with just injection molding. Now, you should know that I've left a lot of features out that are just holes and lightning features. And that's because when you mold a part like this, injection mold it, where you have a large mass and then a small mass, these things end up getting what are called internal stresses, and they bend and they warp and they move all over the place. So we've made it as a large mass that we then come back and machine to the proper dimensions. So let's take a look at that part. This is what the part looks like that we're going to get from our injection molding group. And you can see that there's extra material that we can then machine that fancy seat into. There's extra material that we can machine a pocket into. An extra material that we can machine a pocket into. And extra material that we can machine the O-ring groove and the thread. Okay, so you'll want to make an injection molding drawing for this, like this, and we'll come back and talk about it later. It's not too complex of a drawing. Okay. But then what you're going to want to do is take this and make a copy and create this from it. And you can see it's just, it's just adding some extrusions. Let's see, there's an extrusion that we added. There's another extrusion that was added. There's another extrusion. So it's just taking material away from those. And you'll get a video on how to do that. Okay? And so then there's the extrusion for the O-ring groove, the extrusion for the major diameter of the threads, and there's the coil itself. And we'll go over all of those in lab of how to do those. Okay, so you're going to start with a blank and then machine it to the close dimensions that are needed. So let's take a look at the drawings again. As with every mechanical drawing, there's your main workspace. There are revision notes. There is a title block. On the title block, you'll see the title, the company, the drawing number, how many sheets there are. And since this is D size, we got everything to fit on one. The primary scale. So if it does not say the scale, this is the scale you're going to see. Okay. And in the title in general, I give the long description of the part and then what part of the process this is a drawing for. So this is the seat ring for a 4-inch valve. It's the second check assembly. And this is the injection molded blank. Then we've got the make from. This is something called Noril GTX. We talked about that with the clapper. It's an automotive plastic. I think it's called phenylene. It's very strong. It's very stable. And we use 1.5 pounds of it in that blank. Okay. And there is no stock number for that because we don't stock it. Our vendor, the people that are going to make it, the people we're going to order it from, will stock it for us. Okay. But we want to let them know what to expect. Okay. Here's our standard tolerances. Remember, if a dimension does not have a tolerance listed on it, the radius of 0.25, then we have to come back and go, that was 2 decimal places. So that's going to be 0.25 plus 0.03. So I can, if that radius is as big as 0.28, I can accept it. Or 0.25 minus 0.03. Anywhere between 0.22 and 0.28, when I go about measuring that, will be acceptable. Okay, so all of these, most of these, since it's a blank, have large tolerances, except for this one. Okay, and that's a 0.6 plus or minus 0.01 plus 10 thousandths minus 1 thousandths. And that's off of the original drawing. And I'm not really quite too sure why that's being held so closely. Even though this was my part, I inherited a lot of this drawing. I really don't think it needs to be that tight. Okay, and then this is called the draft angle. That's so that they can pull this off of the core easily. Okay, it also is good for the water flow. So that's what we see, and this is a section view. So remember that when this was put in, this was my base view, and then I made a section view and put it down here. Okay, and the reason the section view does not have letters on it is because it's an orthographic view that's adjacent to the primary view. So you do not need letters on this. This is an understood view per ANSI standards. Now this one does need a view because I don't see where it is, and that's just to show this a little piece of this bottom so that we can apply a note. Okay, put the lettering right there. Okay, now some of the rest of this, again, I really don't think that needs to be 3 decimal places, but it is listed that way on the original drawing, so I put it on there. Notice these ones are not that way. Okay, they're much, much larger. Okay, now these dimensions are, and these can be held with injection molded. If these ones get too big, they won't fit. And so these ones it can be inside a little bit by 0.03, and this one can be outside a little bit by 0.03. Okay? So that's the basis of this. Now you'll notice that this, and you get this model. I've got this model for you, right? And so you just have to figure out how to dimension it kind of like this. I put in a view so that we can make it clear which are going to be machine surfaces for the mold designer. So that's the basics of this. And then flash at parting lines. So injection molds always come in two pieces, and then the mold pulls apart and you can get your part out. And that always leaves a little bit of a flash, a little bit of a little rim. And so this tells them that they have to actually go about and deflash it before they give it to us. And there's lots of ways to do that. We leave that up to the vendor to do. We also give them an inspection priority, the first and last parts of any one run. And then the DIMMs apply after mold shrinkage. This is hot plastic when it goes in, and as it cools, it gets smaller. And so the injection molding company knows all about GTX and how that works and how much it's going to shrink. And this gets a little bit bigger because it shrinks towards the middle of the plastic. This gets a little bit smaller. This gets a little bit shorter. This will actually bend just a little bit. So all of these dimensions change a little bit as it cools off. And so we want to make sure that the vendor knows that these are not the mold dimensions. These are the dimensions of the part after it has shrunk and unrestrained. They don't get to clamp it down flat or anything like that to get it. And STP is standard temperature and pressure. And so that is an inspection term. I don't remember what it is. I think it's 68 degrees Fahrenheit at, I don't know, 1 atmosphere pressure, something like that. I don't really remember all those details. I let the inspectors remember it. And so they'll take two parts, the first and the last part of a run, into the inspection shop and let it sit for a day or 4 hours or 5 hours to come to temperature and pressure, and then they'll inspect the parts. We get to package it in bulk. They don't have to package them separately. And then material certifications are required. So the certification that this was made out of Noril GTX injection mold plastic would be required to come with the parts. Okay, so there we go. That's our review of the blank or the injection mold part. Let's take a look at the machine part. Now this is a fairly complex drawing because lots of stuff is happening all over the place. Here are my two primary views. And I'm not dimensioning much on these, but these just let me know where things are and about how big it is. Now, this dimension here comes from the molded part. So it's in the reference brackets, the reference parentheses. But then I need to make the diameter for the O-ring. And this is what it is. And normally O-rings have different tolerances on it. So that's why this is modified. But this is what works in this part. And so that is the O-ring groove dimension. This detail says, okay, I'm going to tell you about all this stuff in detail B. I'm going to tell you about all of this stuff over here in detail C, because this is just too small. I can't get everything in there. I'm going to machine this zone. Okay, I'm going to machine that entire zone. And detail D is where I'm going to find out about that. So let's look at my detail D. Here it is. This is my detail D that tells me about this pocket that I'm machining. And then I had to make an alternate view over here. And as I look at it, I prefer not to show the entire line. Okay? And so here it is. This tells me the top view. This tells me the other view. I'll talk about the datums in a little bit. Okay? But what happens Well, I'll talk about it now. What happens is everything is relative to this seat. That's the key important part, which I told you about. And so after that's machined, what's called full cleanup, they're going to go a full cleanup and then they're going to machine it down 0.048 inches at 45-degree angle. And this surface, after it's been cleaned up, now becomes A. And it's flat within 5,000ths of an inch. Quite frankly, you can hold that much closer with a mill. You could easily hold 1 or 2 thousandths of an inch flat. Okay? So that becomes my key important point. And then this becomes my next important point. So that dimension there. And I'm not too concerned about the dimension itself. It can be plus or minus 10 thousandths of an inch, but I need it to be parallel to this. I need it to be parallel within 5 thousandths of an inch. Okay, otherwise it doesn't seal properly. And I can get too much of a cut when this goes on and off and on and off and on and off. So now I have two new ones. I have this and I have this B. Okay, and I'm saying that I'm machining that zone. That's my machine zone. Okay, and it's got to be parallel to A. And then I just want a nice clean bore right here that's straight. And so you'll machine that also. So that tells you a lot, right? This one is really important. And then we've got the same thing on the other side. Okay, it's the same thing on the other side where I've got, and I'm going to not show my entire line. So here again, I've got a cutout, which I show right here. There's my cutout. And the cutout goes to 0.172 above the seat. So it's just a rectangular cutout. But then I've got these two little counterbores. This is a counterbore. See what that is there is this right here. Okay, I have to put that hole through there. And then I have to put the counterbore in. And let's see where I talked about the counterbore. Thought I had the counterbore in here somewhere, and now I'm not seeing it. So I'm gonna have to I have to add a view for you. It's amazing when I miss a drawing. I don't have to add a view. I just have to add my counterbore call out right here. Okay, so I'm gonna counterbore to a depth. Whatever I've made here, I'm gonna counterbore it so that I have 0.215 thickness right there. Okay, on either side, and that's called a breakout. That's why I did that. There's a breakout so that I can do. I don't have to do it to a hidden line. Okay, so there we go. I've got those, but I've got my. I could actually call it out here. I could call it out a backside spot face or a backside counterbore, but I think I'll call it out right here. So you'll see that when we get to it. I'll do it as a probably as a leader text, as call that one out. Okay. And so I do the same thing over on this side, right? I have to call out this hole right here. And so I've got the dimensions, and notice how tricky these are. Oops, this one needs a tolerance. Okay, as I'm looking through here, I'm seeing things I have to change. This one is a very close tolerance. And it's a deviation. So I can be a little bit more. So that means now I need to move that. There we go. So got those ones. So those are very critical. These ones need to be fixed too. Um, so I'll go ahead. That one's okay. This one is extremely critical. Good. So you can see as I go through these, sometimes I don't catch everything on my first time through when I do it, but you'll have those on your version of this to be able to do. So what's critical is not so much exactly how it's centered up over this seat because I've got a little bit of room, but this dimension between here and here and these two dimensions are very, very critical as we go. Okay. And so let's see, is there anything else? Now this is interesting. So as I run this is my surface A. This has to be parallel because if it's not, you can imagine if this pin, excuse me, is really out of parallel, then it won't seat properly here on one side of that big clapper and it will on the other. I'll try to get you a visualization of that. It's hard to do, but I'll see if before lab I can create a visualization of that to show you just how badly it affects the seal. This hole has to really be parallel to that. And so when we built this, we actually built a fixture that's set up on this, and we pushed this against the fixture and then drilled these holes so that we were absolutely certain they were parallel. Okay, we actually did much better than 0.005. We were usually getting 2 or 3 thousandths of, and that was basically just tool wander. Tools can wander a little bit. If you can think about a drill coming all the way down here, this small of a drill over that length is pretty hard to do. So we had what was called a drill guide that was part of that fixture that sat in between here. And so it drill through here, and then the drill guide would support it, that long drill bit all the way through here. And then it would do this last part. Okay, so there's lots to machining. You can't just give somebody a drawing and know it's going to work. Somebody's got to figure out how to do it. So this was about a year's worth of work for us to figure out how to reliably make this part so that it would always work. Okay, and so I see a few little things here that could still be cleaned up. This could definitely be brought into here so that this comes into here. When you see the final version of this, I've simplified this drawing since the last time I've made it, which is why I don't already have it drawn all the way for you. And so you'll get a drawing like this. But here we go again. We've got our title block, our make from. Let's see what we're making it from. It's made from Neural GTX. And in this case, we're going to go grab one of those blanks. So this lets the machinist know, go grab that blank right there and set it up. And there would normally be also manufacturing notes on here about the fixture and all that. We're not getting that deep into it. But there's our standard tolerances. There's our revision block. Here's our notes. Now, this one, we're making sure that they use non-petroleum-based fluids when they machine it. Okay, petroleum would actually be okay on this, but often these are done on the same machines as other parts that require non-petroleum based fluids. And so we just call that out just to make sure that you don't cross-contaminate another part with cutting fluids for this part. Okay, inspect first and last parts, plus 1 out of every 100 parts. Again, dimensions apply unrestrained at STP. Now, when you package this thing, we can package it in bulk, but we're saying that this seat is rather delicate, so it needs some sort of a protector as you package it in bulk. And again, that will be up to the manufacturing engineer to do that. And then again, non-abrasive, non-petroleum cleaning methods to get any cutting fluids and little just pieces of gunk that are left on here flashing, get it off. So there we go. There's all about the second check. Again, you're going to machine this pocket, these holes. So you have to model this pocket and these holes. This pocket, this little extra pocket, and this hole, and this thread. Oh, let's take a look at the thread. Where have I called out the thread? Maybe I haven't done that. Oh, here it is over here. So here's the O-ring groove. We've called out the diameter over there. And so it's 0.32 wide. And there's this little rim. And then we've got this thread. And it's an Acme thread. That means it's got a very specific thread angle and a flat tip or flat root. And I'm not sure I've got this all the way right here. It looks like I've got a little problem with it with my model that I'll go back and check out at this part of it. I think most of it's okay. I might have a problem down on this one end of it. But basically, it's got a major diameter, that's this outside. It's got a minor diameter, that's the root. And it's got a pitch diameter. That's sort of in between where when you're doing calculations, that's where the calculations for forces happen. And 3 TPI, 3 threads per inch. So it should be 0.333 from this point to the same common point. Okay? And so I'll show you in lab how to actually create that model of what you have to do to be able to do that. Okay? And there's a couple of different ways. You can either take it down to the root diameter and add material in, or you can take it to the major diameter and subtract material. Okay, so there we go. There's all about the second check.